I'm assuming you guys wanted to go over chapter 6 and 7? Okay, that's what I figured. So I'm going to start by reviewing this chart here, which again is the last page in Dr. Cosper's notes. You guys that have been here before know that I like to focus on frameworks, meat and potatoes, and then kind of build on the specifics from that. And this is a great chart for that. When I took the class, I literally, once I received the quiz on this information, I just kind of brain dumped something very similar to this on the quiz. And that way you can answer any question that he could possibly ask. I will say the only thing that's not on this chart is the why. So why do these reactions prefer a primary haloalkane? So that's the one thing that you have to learn and kind of bring to this. But other than that, all of the talking points are here in one area and it's very organized. So this is a pretty fantastic chart, okay? So I'm going to walk through each page, which corresponds to each reaction, and then I'll refer back to this before we move on to make sure you understand each component. But again, if anything intersects with a reaction, it corresponds to that reaction. Okay? Any questions before we get started? I'm assuming you guys just kind of wanted a quick overview. Okay. So we're going to start with SN2. So SN2, you had, that was all chapter 6 was SN2. I'm going to draw the reaction that's in Dr. Cosper's notes just so we have a good visual. Oh, I didn't get myself in front. That's okay. Okay, so you'll notice around this reaction we have little paragraphs of information that she's provided for us, okay? Some of these are going to repeat themselves, okay? So I'm going to point that out as we go along. The one piece of information that repeats itself each time is the leaving group, okay? The leaving group, we're referring to this X. Does anybody know what the best leaving group is? No. How about this? If you see X in a reaction, do you know what type of element that's referring to? Halogen. Okay, so anytime you see an X, that's a halogen. So fluorine, chlorine, bromine, iodine. Okay. So in terms of the best leaving group, you actually have to kind of go back to the chapter on acids. So the strength of an acid is determined, we talked about two characteristics. What are the two characteristics? It's funny how it just disappears after the quiz in the midterm, right? Okay, so when we're talking about acidity, there's two things. So electronegativity. And the size of your A, okay? And A is just these four right here for just to make it easy. Okay? So all of these are halogens, so they all have pretty close to the same electronegativity. Also, obviously, fluorine has the highest, but all about the same. Which one of these is the largest?
What size?
Yes. Iodine. Iodine is the best leaving group. Okay? Another way to think about it, so leaving group, we want this halogen to come off of this alkyl halide. So it needs to be able to break off. When we're talking about acids, the strength of an acid is determined by how well it breaks apart. So it makes sense that the I of a strong acid is going to be a good leaving group. Does everybody understand that logic? So no matter what reaction we're referring to, the best leaving group is always iodine. And I will say that is a very popular question for him. So I wouldn't, it's definitely going to be on your quiz. So iodine is the best leaving group. That's the one piece of information that kind of corresponds to all reactions, no matter what they are. Okay. So we're going to talk about each mechanism that corresponds to this SN2 reaction. Let's first talk about the name. What does SN2 mean? Substitution, S.
Nucleophile.
Nucleophilic, good. Substitution.
2 molecules.
Okay, bimolecular.
Bimolecular.
What does bimolecular mean? So you said 2 molecules, but 2 molecules what?
Reacting with each other.
Yes.
Combining.
So bimolecular refers to what affects the rate of the reaction. So bimolecular means that concentrations of 2 reactants affect the reaction rate. So the concentration of the nucleophile and the concentration of the alkyl halide both affect reaction rate. Okay, this will change when we move to unimolecular. Okay, does everybody understand the 3 components of the name? Any questions on bimolecular? Okay. If you had to classify this alkyl halide as primary, secondary, or tertiary, what would it be classified as? Primary, okay? Why not secondary? There's 2 carbons here.
Because you would have 3 carbons to be secondary, you would have a carbon attached to 2.
Right, so it's not about the number of carbons, it's about the number of carbons attached to this center carbon. Okay, that is a pretty typical error. Okay, so this is a primary because around this center carbon we only have 1 carbon attached. Even if this was, say, CH2, CH3, it's only referring to the number of carbons that are directly attached. Okay, just some common mistakes that I've seen in the past. Okay, does anybody know why we would want a primary versus, say, a tertiary? Did he talk about football players in doorways? Something?
Steric Hindrance.
Steric Hindrance. Okay, so let's talk about that. So I'm going to show you primary versus tertiary, and we're going to talk about why this one prefers primary. So we've got H's. I'm going to use big circles for methyl groups. Okay. Okay. So the position of this attack, the nucleophile is attacking the center carbon, okay? If we had 3 methyl groups, it would be really hard to attack that center carbon. And that's due to a thing called steric hindrance. So big bulky groups cause steric hindrance. So it's kind of like if a hydrogen were an infant and a methyl group was a linebacker, football linebacker. If there was an infant in the doorway and you were trying to get through the doorway, it would be easy to get around the infant, right? You could maneuver that. If you have a big linebacker blocking the doorway, it's going to be much more difficult to get through that doorway. Okay, so steric hindrance, big bulky groups blocking the way. So for SN2 reactions, we prefer a primary because it allows the nucleophile to attack that center carbon. Does everybody understand the why of why we have a primary here? I'm assuming silence means no questions.
No question.
Okay. So that's the alkyl halide, primary.
Can you pause for 1 second?
Absolutely.
Talk about why it's called an alkyl halide?
Sure, yeah. Okay, so you could also say haloalkane. They're the same thing.
They're interchangeable.
Yep.
Okay.
Halo,
That's totally fine.
alkane, alkyl, halide. So halo and halide are from the same root, and alkyl and alkane, same root.
Okay.
Yep. It's a good question. Take that for granted. Any other questions before I move on to nucleophile size? Okay. So, when we're talking about nucleophiles, you can think of either small nucleophiles or big bulky nucleophiles. So for SN2, because again we need to attack the center carbon, this prefers a small nucleophile. A large one is not going to be able to fit in to attack that center carbon. Okay? So small nucleophile, primary alkyl halide. You good so far? Mm-hmm. All right. So you'll notice here we have a diagram with some dotted lines. Why have I drawn it this way with the nucleophile and the halogen drawn at the same time? There's a word. Starts with a C. Concerted? Never heard of it. Okay. So a concerted reaction means that bonds are being broken and formed at the same time. Okay? So this is not a step-by-step function. Everything is happening at the same time. So this nucleophile is bonding to the carbon at the exact same time the halogen is breaking away from the carbon. This is referred to as a transition state. Which I think if you guys were here when we talked about chapter 2, I think, transition states are kind of that midpoint between your reactants and your products. Okay. I'm going to talk a little bit about the solution that, or the solvent, excuse me, that this reaction likes to occur in. So the solution is called polar aprotic. What does the term aprotic mean? It does. So protic is referring to proton. What does the prefix A mean? Without, or not. Without. Good. So polar without protons. And again, it's important in your mind to remember proton. You may think of it as just something inside the nucleus, but it can also be referred to as H+ ions. So a polar solvent that does not produce H+ ions. So an example of a polar protic solvent would be something like HCl. Hydrochloric acid breaks up into H+ and chlorine minus. So aprotic does not make H+ ions. Okay? So we need to know why we don't want these. Why is this important for this reaction? What charge does our nucleophile have? Negative. And if we had a bunch of H+ floating around, the H+ could tie up our negative nucleophile. Okay? And if you remember, this is a bimolecular reaction. So the concentration of both affects the reaction rate. If we use this up with H+, that reduces the amount of reduces the concentration, so it's going to slow down the entire reaction. So we can't have H+ floating around because it's going to tie up our nucleophile. It's going to slow up our reaction. Does everybody understand why we want polar aprotic instead of polar protic? Yes? Okay. So you'll notice this arrow that I've drawn here. So we have the nucleophile attacking the carbon. This is intentional the way that I've drawn it. Okay? The nucleophile will always attack opposite of the halogen. Okay, so you would never get it attacking here. Okay? This is referred to as a backside attack. So the backside of the halogen. And you'll notice that there's only one arrow. So the nucleophile can't attack at multiple angles or multiple locations. So if you can only attack at one place, you're going to end up with only one product. That's a stereospecific reaction. Do you remember him referring to that in class? Specific. So specific, only one specific place. Only attacking at one spot. So this does affect the absolute configuration. And if you guys remember absolute configuration, so if I asked you guys to find the absolute configuration of this molecule here, how would you start that? It's the first thing you have to do when you're doing absolute configuration.
Find out what's the heaviest.
Good. So out of all of these, what would the heaviest one be?
X.
Right, the halogen. Regardless of which halogen it is, this would always be number 1. Then the carbon, and then the hydrogens. So start here. Would this be R or S? R, because it's clockwise. Okay, if we go to the other side, I know the nucleophile can be a variety of things, but chances are it's going to be greater than carbon. So you could also assume that your nucleophile is going to be number 1, carbon number 2, 3, 4. Counterclockwise, S. So, no matter what you start with, in an SN2 reaction, your final product is going to be the opposite. So if you start with R, you go to S. If you start with S, you go to R. He has been known to ask questions like this. So for example, in an SN2 reaction, your alkyl halide has an S configuration. What is the absolute configuration of the final product? So you need to know that whatever for SN2, regardless of what you start with, it's going to be the opposite in your final product.
And we should always assume that the nucleophile is going to be one. It's going to be heaviest.
Yes. And if he were to ask you that question, he may not give you the full molecule. So like, for example, here you've had to figure it out, but he could just write down the words that I just said and not show you any molecules at all. So, for a recap, SN2 likes primary haloalkanes or primary alkyl halides. Why does it prefer primary over tertiary? Steric hindrance. Okay. It prefers a small nucleophile because it's trying to attack this center carbon. A big bulky nucleophile would not be able to attack at that location. Why do we prefer polar aprotic solvents? What gets tied up if you have protons? Nucleophile, which would slow down the reaction. It's stereospecific because it's a backside attack. It's concerted, which means bonds are broken and formed at the same time, and you form a transition state. Your final product is just a substitution of the nucleophile for whatever your X was. Any questions on SN2? That's chapter 6.
That's it?
That's chapter 6. You only talk about SN2 in chapter 6. Chapter 7 is the rest of these reactions. Okay?
And what you said it was called absolute
Configuration.
configurations.
Okay. I'm going to erase this. So the next one, we're going to stick with bimolecular. We're going to move on to E2. So E2. 2 we know means bimolecular, same thing as SN2. What does the E stand for? Elimination. So elimination, that you should know that that just means that we're removing something. That's another thing, like we're pulling something off of these carbons. So you'll notice in our little chart that a lot of the characteristics that I just explained for SN2 also correspond to E2. And the reasoning is identical as well. So things like the solvent, the stereospecific, concerted, all those are identical between bimolecular reactions. So the only thing that's changed is the size of the nucleophile and our final product. Okay? So here now we have a big, bulky nucleophile. And the reason that we can do that is our positioning has changed on where this reaction is taking place. So this nucleophile is actually attacking this hydrogen. And it's this hydrogen specifically. It's important, and I've actually drawn both here. I don't know if I can put them in both the same. Okay. So when we're looking at SN2 versus E2, you'll notice that in substitution, you're always attacking the carbon that's bonded to the halogen, that center carbon. For elimination, you're always attacking the peripheral hydrogens. We're going to go over the unimolecular, so don't get caught up in that, but I'm just referring to where this reaction is taking place. So we're no longer attacking that center carbon, we're attacking this outside hydrogen. So that's why we no longer need a small nucleophile. We're not worrying about trying to fit in here to attack the carbon, so we can have a much bigger nucleophile in this case. The orientation of this is very important. You'll notice that the hydrogen is kind of on the opposite side of the halogen here, and that is done intentionally. This is referred to as a topside attack versus a backside attack. The nucleophile can only attack that one hydrogen. It can't just pick whatever hydrogen it wants. It has to be the one that's opposite the halogen. In the concerted transition state, so we've got the nucleophile bonding to this hydrogen. As this bond is being broken, the halogen is also the bond being broken. That leaves these carbons with only 3 bonds. So that's going to drive a carbon-carbon double bond. So we've got formed, broken, formed, broken. Probably colors would work better. So the red bonds are formed, black bonds are being broken. So again, the removal of the hydrogen and the halogen forms a carbon-carbon double bond, which was referred to as an alkene.
What were the other red ones up there? I was trying to listen.
Oh, so nucleophile bonded to the hydrogen, and then carbon-carbon.
Okay.
So both of those are being formed. So again, things that have stayed the same. Still a primary alkyl halide, still concerted, still has a transition state, still polar aprotic solvent. Differences being big bulky nucleophile and an alkene as your final product.
Is this apolar or polar?
Polar aprotic.
Oh.
All of these are polar. So again, primary, big because we're no longer worried about attacking that center carbon, we're only worried about the peripheral hydrogens. Same reasoning, stereospecific because it's a top side, this one is a back side, topside attack. pulls off one of the hydrogens, the halogen comes off, and our final product is an alkene. How do we feel about E2 and SN2? Lots of similarities, right? All the hard stuff is similar. Now we're going to move on to where the hard stuff is not similar.
Would E2 ever happen with a small nucleophile? Since it's on the edge?
If it was a strong, we're going to talk about basicity because that's typically not something that he focuses a lot on, but I know he talked about it and it is in the book. So actually the strength of the base is a bigger indicator than the size.
Okay.
So if it was a strong, small nucleophile, it would probably go elimination.
Okay.
He would not give you that situation. I'm going to move on to SN1. Okay, so we know that SN stands for substitution nucleophilic. What does the 1 stand for?
Unimolecular.
Unimolecular, good. So how does that differ from bimolecular?
Only the concentration of what's the word I'm looking for?
Molecule?
One
Reactant?
reactant.
There you go.
Plays a part in the speed.
Rate, yes, speed, rate, excellent, good. So unimolecular, we're only focusing on one. Do you think that that is the one molecule the rate is based off of? Would that be the nucleophile or the alkyl halide?
Alkyl halide.
Very good. Was that a guess or did you know that?
No, I remember hearing that.
Excellent, very good, very good. I mean, it's 50% chance either way, but excellent. I'm glad you remembered that. That's awesome. Okay. So a couple things before we jump in this. You'll notice that we have a carbon with a positive on it. Okay, this is a carbocation.
Are we gonna have to know like what orbital that is and all that?
You mean so you may be asked about the shape, so we can talk about how to figure that out. Basically, it's a hybridized sp orbital that this positive charge is located in. He won't ask you about that. So if you guys remember free radical halogenation, okay, we talked a lot about carbon radicals. A lot of the same rules about stability apply directly to carbocations and even to carbanium ions once you get to those. So it may be helpful to just kind of think of this as a carbon radical. It's not a carbon radical, there is no free electron, but this, in terms of stability, they're identical, okay? So I would think of it that way as you're studying. So you'll notice that I have 2 steps here. Step 1 and step 2. Is this a concerted reaction? No. For a concerted reaction, everything happens in 1 step, okay? So the fact that we have 2 different steps means that this cannot be concerted, okay? So that's already one difference between unimolecular and bimolecular. You'll notice in this first step, we just have the alkyl halide. Literally, this first step is just the X coming off. When we pull that X off, the X is going to take 2 electrons with it, and that's what leaves this carbon with its positive charge, okay? Now, you said that the rate is determined by the concentration of the alkyl halide, and you are absolutely correct. That would make step 1 the rate determining step. So depending on how fast the halogen is removed, that determines the speed of the entire reaction. If we have iodine on here and it falls off readily, the entire reaction will run quickly. If we have fluorine and it takes a while for the halogen to be removed, the entire reaction is going to be slowed down, regardless of how much nucleophile we have. Okay. You'll notice here that we have a tertiary right? 1, 2, 3 carbons attached to this center carbon. Why do you think we have a tertiary alkyl halide instead of a primary?
The most stable.
Okay, good. So going back to free radicals. So it makes the most stable carbocation, just like it would make the most stable free radical. So you need tertiary because it makes the most stable carbocation. Bonus points to whoever can remember the force that stabilizes the carbocation. Hyperconjugation, very good. Okay. The more methyl groups you have around that center carbon, the more hyperconjugation you have. So tertiary would be the most stable. Okay. Based off of the arrows that I just drew, would this reaction be stereospecific or not stereospecific? You guys are cheaters looking at the chart.
Not.
Why?
Because it can go in there or it can go in there.
Good. Okay, so automatically if there is more than one area that the attack can take place, that means the reaction is not stereospecific. Okay. That also means that we're going to end up with two different products. Half of the nucleophile is going to attack from the top side, the other half is going to attack from the bottom side. So we're going to get 50% with this orientation and 50% with this orientation. What is the term for the solution that has 50% of two enantiomers? Racemic. Okay? So the final product is going to be a racemic mixture. These are not technically enantiomers of each other. Don't let that confuse you. Just 50% of two enantiomers is going to give you a racemic mixture. Okay. In terms of the nucleophile size, we're still trying to attack that center carbon, and if you remember from my wonderful drawing with the big circles, okay, you're going to need a small nucleophile to get past those methyl groups. So definitely a small nucleophile here. Some other differences have to do with the solvent that we're going to use. For this reaction, they prefer polar protic. What was our concern with using polar protic solvents when we were talking about bimolecular reactions? Why didn't we want H pluses?
It was going to tie up the nucleophile.
Okay, why aren't we concerned about that with this reaction?
Because we have a carbocation that already has a carbon.
I'm more thinking, so if we have hydrogens that react with this nucleophile, is that going to affect the rate of the reaction?
No, it's a rate determining step with number one.
Good, okay, so this is a unimolecular reaction. The rate is only based off the concentration of this. So if some of our nucleophile gets used up by some floating hydrogens, that's okay, it's not going to slow us down. Dr. Cosper's notes also talks about the fact that polar protic solvents help this carbocation form. It helps keep it stable. So that's another component to understand. Okay, any questions on any of this?
Just repeat what you just.
What I just said? Yep. No, not a problem. Polar protic solvents. So we don't care about the nucleophile getting used up in this case because it's not going to affect the rate. Polar protic solvents also help the carbocation form and help stabilize it. And Dr. Cosper does put that in her notes. So quick recap. SN1, substitution nucleophilic unimolecular, only based off of the concentration of the alkyl halide. We want a tertiary haloalkane because
Makes the most stable carbocation.
most stable carbocation, very good. We still need a small nucleophile because we're attacking that center carbon and we've got a lot of steric hindrance going on there. We use a polar protic solvent because it helps form and stabilize the carbocation, and it doesn't matter if we use up some nucleophile in the process. It's not stereospecific because you can have a top or bottom side attack. There are 2 steps, and there's a carbocation intermediate versus a transition state. Do we all understand those different components? Yes?
It makes sense, but I'm just thinking like, since for this one in SN1 we need a small what to attack the center carbon?
Small nucleophile.
Nucleophile? Okay, yeah. So that's kind of like weird because it's attacking the center carbon. So wouldn't you want like something bigger to attack?
So let's take a look here, because it has to do with Steric Hindrance again, right? So if I draw my, so I've got methyl group, methyl group, methyl group. So I've got big bulky groups surrounding that carbon, okay? You need a small nucleophile to be able to get in between those methyl groups, okay? If you have a big bulky group, there's no way it's going to be able to get past those methyl groups. Good question, though. Any other questions? Can move on to E1. Can erase everything.
Yeah.
Okay. Oh, I should have kept that. That was dumb. Okay. Okay. Actually, before we move on, somebody did ask about, wasn't a complete question about shape, but I think it would be a good thing to go over. So I know a lot of students have difficulty with SP, SP2, SP3, and just looking at something and identifying. So why don't we practice that with this reaction, because it is a good example. So if I asked you for the orbital hybridization of this center carbon, does anybody feel comfortable telling me, would it be SP, SP2, or SP3? SP3, okay, that was very confident. Do you want to tell me why you know that? Or what method you use to figure that out? You're right.
I don't want to explain it, I just kind of know.
You just know it. Okay, is anybody unsure of how to do this, or are you worried about it when it comes up on a quiz? Okay, so it is SP3. I'm going to tell you my method of doing it, okay? And it has to do with just counting the number of attachments. Okay, but you do have to understand a little bit about orbitals. So, without talking about orbital hybridization, in each energy level, how many s orbitals are there? It's actually one s, and there's 3 p's. Okay? So, how many attachments does this carbon have? 4 attachments. So, you start with your 1s, and then you count your p's out until you get to the number of attachments. So, s, P, P, P. 1, 2, 3, 4. SP3. Okay? Let's take a look at the center carbon here. Okay? So I don't want the orbital to confuse you, but essentially we only have 3 attachments. Start with your S. 1, 2, 3. SP2. This carbon here, I know there's 4 bonds, but how many attachments are there? 3 attachments. SP2. How many attachments? SP.
That's way simpler.
So, now you'll never have to worry again. But he could absolutely ask you the shapes or the orbital hybridization. Chances are it's going to be of the carbocation because he wants you to understand the shape. But he could ask about any of these structures. So just so you're aware. Okay, so now we're in E1. So elimination unimolecular. So again, a lot of the components are going to be identical to SN1. You'll even notice that step 1 is truly identical. We haven't changed anything. It's still the rate determining step. The halogen is removed and we make a carbocation. Nothing has changed. We still want a tertiary because it makes the most stable carbocation, and it's still stabilized by hyperconjugation. Okay?
What's the arrow over the X?
Oh, so that's just referring to the dipole. So the X is more negative, carbon's more positive. Now again, just like when we were looking at SN2 versus E2, the big difference is the size of your nucleophile. Oh yeah.
Some of the paper says equal substitution.
Yeah, that's a typo. Good catch. So the only thing that's changing here is the size of the nucleophile. So we went from having a small nucleophile to a big nucleophile. And really, the reasoning behind that is where we're attacking. So I've drawn it out here, but just as a comparison, in SN1, the nucleophile was attacking the center carbon, so it had to be small to get in there. In our elimination reaction, we're attacking the peripheral hydrogen. So we can afford to have a big bulky nucleophile because we're not worried about getting in here. We're just attacking the hydrogens on the outside. Does everybody understand that? Okay. So again, just like SN1, this isn't stereospecific because we can attack any of those hydrogens. There isn't a specific hydrogen that we're looking for. When we pull off one of those hydrogens, this carbon already has only 3 bonds. That will make this carbon have 3 bonds, and that's going to drive this carbon-carbon double bond, making an alkene.
Why don't we just pick up the hydrogen?
A hydrogen? What charge does a hydrogen have again? Would a positive want to go to a positive? No, it wouldn't. Way to think outside the box, though. So again, this is a stepwise reaction. It's not stereospecific. It's determined by the concentration of your alkyl halide, which is your rate determining step. You need polar Protic solvents for the same exact reason as you do in SN1. It stabilizes and helps form the carbocation. A tertiary haloalkane makes the most stable carbocation. Big bulky nucleophile because we're attacking the peripheral hydrogens. And our final product is an alkene. That's chapter 7. I included basicity because I had 2 questions on it earlier today. So technically, if he did ask you about that, a weak base would typically go substitution. A strong base would typically go elimination. So if you could just add that to the chart that you have, and like I said, pretty much just brain dump when you get to that quiz.
Okay, so does the concentration of the nucleophile affect the rate of the reaction?
For which one?
For the E1?
So you tell me.
I mean, I don't think it does.
So is it unimolecular or bimolecular? Uni. And so the rate determining step for both E1 and SN1 regards the alkyl halide. So the nucleophile, the concentration doesn't affect it at all.
Can you push that?
Oh, yep.
So where does our halogen group go?
It's floating around.
It's off in space.
It's right here.
In and out. Okay.
Right there. Just want to make sure I didn't forget anything. Yeah, this covers it.
Will you run through from the beginning to the end of this sentence one by
Of
all the way through?
E1 specifically?
Of E1.
Sure, absolutely. Okay. So, E1, elimination unimolecular. You have a tertiary alkyl halide. The first step is the rate determining step where the halogen is removed, creating a carbocation. The carbocation reacts with a nucleophile that it can attack any of the peripheral hydrogens, so it's not stereospecific. When it pulls off one of those hydrogens, it creates a second carbon with only 3 bonds, which drives a carbon-carbon double bond, making an alkene. Because there's 2 steps, it's a stepwise, not concerted, and it has a carbocation intermediate instead of a transition state. And it prefers a polar protic solvent because the protons help stabilize the carbocation, and it tying up with the nucleophile won't affect the rate of the reaction.
Mm-hmm.
I can throw out some questions.
Yeah.
We have 15 minutes. Can I ask everybody to put away their charts?
Our notes now?
You can keep your notes, just don't have the chart out, because that's too easy.
Well, we memorized the chart, then we'll probably do it, right?
Exactly, yeah.
Very cool.
Okay. What type of solvent is used in an E2 reaction? Polar aprotic, good. Why do SN1 reactions prefer tertiary alkyl halides?
Creates a stable carbonyl.
Excellent, good. What is the final product of an elimination reaction? Great. If a reaction occurs in 1 steps with bonds being broken and formed at the same time, what is the term for that? Excellent. What is the rate determining step of E1 of an E1 reaction? Somebody who hasn't answered yet. Oh, did you already say it?
Yeah, I didn't hear you.
Okay. What is the rate determining step of an E1 reaction? Step 1, good.
I don't know if that's what you wanted to say. I was like thinking that in my head. Like, is that
So if he asked for more detail, like maybe or what is involved in the rate determining step of an E1 reaction, how would you answer that?
the halogen removes?
Good, so the halogen is removed from the alkyl halide. Something simple like that could get you the points. If a big bulky nucleophile reacts with a primary alkyl halide, what mechanism would most likely occur? Wait, sorry.
The backside.
More of just, so he would give you, so I said big bulky and primary. So he would then say, you know, SN2, E2, SN1, E1. Which one of those? So big bulky nucleophile, primary alkyl halide. Excellent, very good. What do polar protic solvents release that polar aprotic solvents do not? Good, or protons, however way. That might be a multiple choice where you have to circle it. Why do SN2 reactions prefer primary alkyl halides?
They gotta get in.
So what's the term? Why wouldn't you want a tertiary? Steric hindrance, there you go. What type of attack occurs in an SN2 reaction? Backside. How about in E2? Good. Are E1 reactions not stereospecific or stereospecific? Not stereospecific. What force stabilizes carbocations? Good. I feel like I've asked you every possible question.
Awesome. I know. Good. I feel way better on this now.
Great.
Like, this is not.
It's not as scary as you
No.
know.
Not Not at all. So you said E2, it attacks topside?
Yes. Yep, that one specific hydrogen.
And then for E2, we had like the nucleophile to the hydrogen to the carbon.
Mhm.
It's taking that hydrogen off and bonding to the carbon? Like what's going on in the transition state?
Sure, yeah, let me redraw it. This is E2 you said?
Yeah.
So we've got, I did it again, colors.
And one more.
You're right. 2 more hydrogens. What's wrong with me, guys? Okay. So red is forming, black is breaking. So nucleophile is pulling the hydrogen off, the halogen is falling off on its own, and that drives a bond between the 2 carbons here. So basically, this coming off leaves this carbon with 3 bonds, this coming off leaves this carbon with 3 bonds.
Okay, so that's driving the double bond.
Yep. So both of those carbons require an additional bond to be stable. Oh, I did get a good question, and I wasn't positive on the answer. Somebody today asked me, what if you had a secondary haloalkane? What would drive it? And for that, I'm pretty sure if he were to give you a secondary haloalkane, he would give you some other mechanism that would kind of help you figure out what process it would follow. Like, for example, he might say it's a big nucleophile and it's in a polar protic solvent. So chances are it would run E1. But I would confirm with him on that because I don't recall. So essentially, if you had a secondary, it would run slightly slower here because of the steric hindrance, but it would run slower here as well because it's not as stable of a carbocation. I don't know which would affect the reaction more. So that would be a good question for him. Because I do remember in the past, I feel like he did ask a quiz question that involved secondary, and I can't remember. I'd have to review the textbook, and I haven't had a chance to do that. So since you have some time before the quiz, that might be a good question to ask in class.
So is SN1 the only one that makes a racemic mixture?
Yes. These only end up with one type of product. So you couldn't have racemic if you only had one type of product. And then alkenes you can't have enantiomers of, so you wouldn't be able to form. So yes, SN1. And then, so essentially the substitution, these are the only ones that really involve some stereochemistry changes. So SN2, R to S, S to R, and then like you said, racemic. Because these are making alkenes, you really don't see any stereochemical changes.
And then is he gonna ask us, like, give us a good example of a big nucleophile?
So that hasn't historically been something he's focused on.
Okay.
I'd be really surprised if he were to do that. And I'm sure even if you were to go back in his notes, he may give you an example here or there, but he doesn't go in depth in that.
Yeah.
So I don't foresee that being something he would ask. He's more concerned that if he tells you the size, you know the pattern, I guess is the best way to put it.
So E2 is stereo-specific?
Yes. Because it's a topside attack. It can only attack from the top hydrogen. It is 504. I know you said you had to leave to go to Worcester. Okay.
355. I think you're watching me.
5 minutes of 4.
Yeah.
Oh, I thought you said 5 something.
Oh, no. That would be really wrong.
Yeah.
And this would have been a much longer session than I planned it. Any other questions that you guys can think of? Any questions from the midterm that you maybe still don't understand? I know you don't get to keep them, but okay.
Does he reuse midterm questions on his final?
I mean, I think there were definitely some quiz questions on your midterm, so there is possibly a chance. They may not be copy and pasted, but they could be essentially identical. Depending on who comes next week, we may review 6 and 7 again, but if it's everybody that's been here this week and there are no questions on 6 and 7, we could jump on to 8. So whatever you guys want to do next week.